In chapter 12.3, we're going to be discussing the dot and cross products, which are two vector algebra operations. So they're just more mathematical operations that we're going to add to our library of operations. So they're two operations that we use on vectors. Right? Just like we can multiply and divide scalars, these are operations specifically for on vectors. And so we're just going to begin by taking two example vectors. We'll have v and u. And for this entire course, the notation I'll use for vectors is the letter with a little arrow above it, because I can't write in bold font, so I'll just use that for my vector notation. So let's just assume we have two vectors like this. Here's our u vector and our v vector. There's a couple different operations we might want to do. So the first one is the dot product. And the dot product is an operation that can tell us something about how parallel two vectors are. So it really is telling us tells us about how parallel they are. Two vectors are. And the equation for it is written like this. We write the dot product as u dotted with v. So we just use that dot notation to indicate we're doing the dot product between two vectors. And the equation is u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them, where the cosine of theta, that angle is right here. So that's the angle that we're taking the cosine of. And so you can see that when the two vectors are in the same direction, that'll be an angle of 0, and cosine of 0 is 1, so it maximizes the dot product. And if they're perpendicular, then you have an angle of pi halves, and cosine of pi halves is 0, so that'll minimize the dot product. So the dot product is biggest when the vectors are parallel, and it is 0 when they are perpendicular, and it'll range between 0 and 1. So if you notice, the output of the dot product is a scalar, right? So it's just a number. So the output is a scalar. And another way to calculate the dot product is if you don't know the specific angle between two vectors, then you can also write it like this. So it's also calculated, and this is the way we'll usually be calculating the dot product, is by summing the product of the like terms. So it's also calculated as this. So u dot v is equal to u1 times v1 plus u2 times v2 plus u3 times v3. And if your vector had 5 components, you would continue the pattern, and you're just multiplying the like parts. So multiplying v1 by u1, adding v2 times u2, v3 times u3. And another property of the dot product is it is commutative, which means that, so it is commutative, which just means that u dot v, so the dot product of u and v, is also equal to the reversed order, so v dot u. So you can do either order. It doesn't matter what order you do it in. And so that's kind of how we compute the dot product. And like I mentioned earlier, this is the most common way that we're going to calculate the dot product between two vectors. Now, like I mentioned, for orthogonal vectors, we get a very special result. So if u and v are orthogonal, or they're perpendicular, then you know that theta, the angle between them, will be pi half degrees, or pi half radians. So we could imagine we have v and u, and because that angle is pi halves, the cosine will be 0, so the entire result of the dot product will be 0. So u dot v in this case will equal 0. And that is true for any orthogonal vector. So this is true for any orthogonal vector. So oftentimes when we're doing vector calculus or vector algebra, we'll need to tell or determine if two vectors are orthogonal, and the easiest way to do that is to take the dot product between the two and check to see if it's 0. So this is a great way to use it to check if two vectors are in fact orthogonal. So that's a really neat and useful property of the dot product, is checking for orthogonality. Another application of the dot product is to find the specific angle between two vectors. And if we rearrange this equation we have up here, we can rearrange this equation and use the law of cosines. You can find the angle between two vectors if you don't know it. So the angle between two vectors is the inverse cosine of the dot product of two vectors divided by the products of their magnitudes. So the magnitude of u times the magnitude of v. And remember, I'm assuming you already know some of the basic operations with vectors, but just as a reminder, to get the magnitude of a vector, for example, the magnitude of u is equal to the square root of the sum of the squares of the components. So it's the square root of the sums of the squares. So it's u1 squared plus u2 squared plus u3 squared. That gives you the magnitude, or the length of the vector. So that can give you the angle between two vectors. And then the last idea is the dot product really is also a projection of one vector onto another. It's how much of one vector is in the direction of another, right? And like I mentioned, when two vectors are parallel, right, if you have u and you also have v in this direction, then that dot product is going to be maximized because all of u is in the same direction as v. So that's dot product is max. And then when they're orthogonal, it's 0. And so this idea of projecting one vector onto another looks like this. So say we have a v vector and a u vector, like that. Then we can write the notation for it is the projection of u, onto v, and that would be how much of the u vector is in the direction of v. So in this case, it looks like this. because that's the amount of u in the v direction. So the analogy that's often used is if you shine a light perpendicular to the vector you're finding the projection of, then the shadow that's casted on the other vector is its projection. So you can imagine we have like a little light source here. Then the shadow that's casted by you, all right, we'll cast a little shadow. That'll be equal to the length of that projection on the v vector. So that is the projection of u onto v. And the equation for finding that vector is the dot product of the two, so u dotted with v, divided by the magnitude of v squared times the v vector. And so that's how you find the amount of u in the v direction. And that's called the projection of u onto v. So these are all the neat applications and properties of the dot product. And now we'll move on to the cross product. And we can compare and contrast these two different operations. So the cross product is written like this. So if we keep our u and v example vectors, then the cross product is u cross v. And so we use that cross, or the x symbol, for the cross product. And what that is equal to is the magnitude of u times the magnitude of v times the sine of the angle between them times the normal vector. And so let's break down that equation. You might immediately recognize that it looks very similar to the dot product equation, which was magnitude of u times magnitude of v times the cosine of the angle, where this one is times the sine of the angle. And so if you think back to that relationship between the angle and when the result was 0 or when it was maximized, those are really going to be inversed for the cross product. And so the cross product is really telling us about how perpendicular two vectors are. Right, and so when two vectors are completely orthogonal, then the cross product will be maximized. So in this case, in this example, if we had u and v like this, then the cross product is max. And similarly, when they're parallel, the cross product is 0. Right, because the angle between them would be 0, and sine of 0 is 0, so that would negate the entire cross product. And now let's take a look at the outside. So it's magnitude of u times magnitude of v times the sine of the angle between them, all of that in the normal direction. And so the difference here is that the cross product is actually a vector. So the resultant is a vector. So when you take the cross product between two vectors, the output is another vector. And the vector is always normal to both the vectors you took the cross product of. So this in vector is a direction normal to both u and v, the two vectors you took the cross product of. And so in this case, if you imagined u and v lying in the plane of this page, then the only vector you can find that would be perpendicular to both of them is actually to come out of the page into the third dimension and kind of have a vector pointing straight up. And we use the little circle with a dot in it to notate a vector pointing straight out at us. And I can do another example in perspective. So if I did just a little perspective drawing, here's U, and here's V. Those are in the same plane. Then the cross product between U and V would be that. So that's U cross V. Would be that vector, where the result is normal to both. We saw that the dot product was commutative, so you could switch the order. The cross product is actually anti-communicative, which means, if we wrote that down mathematically, so it's anti, which means that U cross V is equal to negative V cross U. So if you switch the order of taking the cross product, then the magnitude of the answer will be the same, but the direction, the vector points will be in the negative or the opposite direction. So it's just same magnitude, opposite sign. Now, one of the interesting geometric properties of the cross product is it gives you the area of a parallelogram spanned by the two vectors. So for example, if we go back to our U and V vectors, like this, then we know taking the cross product between the two will give us a vector in this direction, right, the normal direction to both of them, but the magnitude of it is equal to the area of this parallelogram made by sliding the U vector up in the direction of V, right? So the parallelogram that this traces out, the area of it is equal to the magnitude of the cross product. So this area here is equal to the magnitude of U crossed with V. So that's the length of this vector. And again, the direction is in that normal direction that's perpendicular to both U and V. And so just like there was an easier way to calculate the dot product, there's the conventional way to calculate the cross product as well, given that you don't know this angle between them. If you're just given two vectors, very rarely will you actually know the angle between the two. So we need a way to calculate it without knowing the sign of the angle. And so we use this formula. So to calculate, we get U crossed with V is equal to the determinant of a 3x3 matrix, where the top row is your three unit vectors in the I, J, and K directions, right, where, remember from linear algebra, those are the three vectors in each of the unit directions. So if we have like our coordinates system, which is like X, Y, and Z, then this is I. I is the unit vector in the X direction. J is the unit vector in the Y direction. And K is the unit vector in the Z direction. So we have our three unit vectors as the top row. And then you just put in the components of your two vectors in the next two rows. So you have U1, U2, and U3. And then we have V1, V2, and V3 as the components down here. And so if you take the determinant of this matrix, then you'll get a vector resultant that is the cross product between them with both the magnitude and the correct direction. So that's how you calculate the cross product. So let's look at two example problems that'll both use applications of the dot and cross product, so we can see how they're useful. So this first one is asking us to find the work done by a force, which is 5 newtons in the x direction, when we move along a path from the origin to this point. So let's just sketch out a little picture of what's going on. So we have a force which is 5I. So it's just 5 newtons in the x direction. So here's our force. Here's our force F. And then the path we're taking is from the origin to the point 3, 2. So here's the point 3, 2. So there's our path. And then this is the force pushing along that path. So if you were moving a particle from the origin to that point, and this is the force moving. Now, if you remember, work is only accumulated when the force and the direction of motion are in the same direction, right? That's important. So work, if you remember, it's equal to the force times your direction times the cosine of the angle between them. Now that looks very familiar to the dot product formula. It's your force direction times the cosine of the angle. And so because the dot product is telling us how much of one vector is in the direction of another, we can use the dot product to find how much of this force is acting in our path of motion. So we know that work is just equal to the force dotted with a vector that's in the direction of motion. So I'll call this a vector here. That'll be D. So to solve this problem, first I'm going to find the vector that represents D, and that's really easy. So D will just equal, that'll be 3I plus 2J. And our force vector is just 5I. So now let's dot them together to get work. So work is equal to 5I dotted with 3I plus 2J. And so now we just multiply like terms and add them together. So that'll be 5 times 3 plus 0 times 2. So in that case we get 15. So that's the amount of work it takes to move a particle along that path with a force of just 5 newtons in the I direction. So that's how we can use the dot product. And now this one, we'll use another one of our operations. So in example 2, we're asked to find the area of the triangle made by the points, these 3 points. So again, let's draw a picture. And I know these points have 3 components, so I'm going to draw a 3-dimensional space. Just so we can sketch out what's going on. So A is at the origin. The point B is at -1x, 1y, -1z. So that's -1, 1, -1. So that's somewhere down here. Actually, let me bring this out a little bit more. So it's kind of like down there. And then we also have the point 3, 0, 3. So 3, 3. So we have this. That's where this point is. and this point is at 1. Oh, this is C. Let me see if I can find a way to sketch this B point. So it's -1, 1, -1. So we have this. Oops. So 1, -1, -1. So it should actually be down here. And so we have this triangle. Oops. Kind of made here. So this is a triangle in 3 dimensions that's kind of skewed. It would be pretty complicated using just the base times height divided by 2 formula to find the area of this triangle. But luckily we know another operation that has something to do with area between 2 vectors. So if you remember the cross product, the magnitude of the cross product is equal to the parallelogram made by 2 vectors. And so if we want the triangle between 3 points, we could just find 2 vectors that connect the 3 points and divide it by 2, right? And that will be the area of this triangle. So the area of a triangle that's equal to half the magnitude of the cross product of 2 vectors. So all we need to do is find 2 vectors u and v that we can cross together to take the cross product. So one vector we can do is this AC vector, and the other one can be AB, right? This is the B point. Right, when we cross them together, we'll get the area of that larger parallelogram, and then just take half of it. So we first have the vector AC. And in that case, AC is just going to be the vector, what is that, 3, 0, 3. And the vector AB is -1, 1, -1. Now these were really easy to make because I chose the origin point to be the central point of the 2 vectors, so it was just their components. Now we can take the cross product between the 2 of them. So we'll do AB cross AC. So we know that area is going to equal 1/2 times the magnitude of AB cross AC. And so we know that that's going to be half the determinant of our 3 by 3 matrix. I keep writing my I's as J's. I, J, K. And then our components are for AB, -1, 1, -1, and then 3, 0, 3. So let's do this calculation down here. So that's going to be 1/2 times. Now, remember our rules for calculating the determinant of a 3 by 3 matrix. That's the cofactor expansion rule, where you do I times the product of this minus the product of that. And we'll just repeat that pattern. So we have 3 plus 1 times I. And then remember minus, we switch signs. So that'll be, sorry, that's -1 times 0. So that's 3 plus 0, or 3 minus 0 times I, minus, now we're doing -1 times 3, -1 times 3. So that'll be minus -3 minus plus 3. So minus a negative in the j direction. And then we get plus, for k, we'll have -1 times 0 is 0, minus 3 in the k direction. And so this simplifies down to, oh, it's 1/2 the magnitude. So that's 3i minus 3k. And so let's calculate the magnitude of 3i minus 3k. Which is going to be 1/2 times the square root of 3 squared plus 3 plus -3 squared, which is just 1/2 times the square root of 18. It's 1/2 root 18. Which I believe can simplify down. So we have 18 is 3. 3 times 3 times 2. So that's 3 root 2 over 2. So that's 3 root 2 over 2. So that's the simplified exact answer for the area of the triangle made by these 3 points. And we use the property of the cross product's magnitude being the area of the parallelogram to find that area. So we just cut it in half to get just the area. And then as a review from this one, we use the property of the dot product telling us how much of one vector is acting in the direction of another to apply that to finding work.